3 case studies showing ICT supporting hard-to-teach topics in secondary science. Using data logging equipment to capture real-time experimental data, using curriculum resources on a virtual learning environment, and using comic strips and animations to illustrate an investigation.
We've been doing data logging at this school since 2003, and we have a whole collection of data loggers. For example, today we're going to be showing the use of a sound sensor, a carbon dioxide sensor, an oxygen sensor, a humidity sensor, a light gate, and all these things, just pretty much like every data logger we have here, can be connected to a laptop. And not only that, we also have these PDAs, which means we can attach any of these sensors to it and we can do some remote sensing. But the beauty of it is that the pupils can collect data, use the data, interpret the data and evaluate in real time what they're doing, and that's what the real benefit is of data logging. And what you're going to have to do is
Science teacher Paul Priest is going to demonstrate a classic combustion experiment to his Year 7s, but with the addition of some data logging equipment.
We have in there a thing that detects water, a sensor which detects oxygen, and we have the sensor at the bottom which detects carbon dioxide. And the computer is going to plot for me how much oxygen is in there, how much water is in there, and how much carbon dioxide is in there. So I'm going to connect these sensors up first. So, first of all, I'm going to attach my oxygen sensor here, my CO2 sensor, and my water sensor. So our carbon dioxide is not changing, our water is not changing, and neither is our oxygen. Okay, staying the same. So I'm going to put the candle in. I'm going to watch what's happened and see if you can use very quickly the ideas of what happens with the graph to explain what is going on. Okay? So what's rising?
The blue.
Moana?
The humidity.
The humidity, good. What's that detecting?
The water.
Thank you, Cameron. Okay, so we are detecting water. What is happening to the amount of carbon dioxide inside the bell jar?
It's increasing.
It's increasing, thank you. So the carbon dioxide level is going up. The oxygen level is going
down.
Down, thank you. Okay, so the oxygen level is going down. The humidity's gone up high. Look how high the humidity's gone.
Ooh.
Okay, so what does that mean we are using up? Moana.
Is it the oxygen?
Well done, Moana. It's the oxygen. What are we producing?
Is it carbon dioxide?
It is, well done. And what else are we producing? What else are we producing? Think about what's the other one that's gone up?
Is it the humidity?
Humidity. And what does the humidity detect? You drink it?
The water.
The water. Thank you very much. Okay. I know the candle's gone out. Okay, thank you. There's a lot of taken on trust and on what the teacher says when you talk about combustion. So demonstrating that how the water is produced and the only thing that is actually happening is something is burning. So you can actually show the water levels increasing and show that the carbon dioxide level is increasing and show the oxygen level is dropping is a really crucial point. And then they start to appreciate looking at a graph to see how things change, that if it's going up, it must be being produced. If it's going down, it must be being used up. So they start to now appreciate what a chemical reaction is, what reactants are, what products are, even if they don't fully understand all the language we would normally use when we're talking about science. So that's the benefit of using the data loggers.
These Year 8s are going to use handheld PDAs connected to a sound sensor to investigate sound levels.
Okay. You should have a blue screen that looks like that. What we do then is we go to the start, and then you go to Programs, once you hit the start button, and then there's a folder called Sensing Science. If you click on that, click on Graph, and then you should get a graph being produced. Okay? It's playing now. PDAs are really, really useful pieces of kit. And what's nice about them is that they know how to use technology. They don't have any problems with that. And the idea you can plug and play straight away into a sensor, and you can start to actually take actual measurements, and it plots the graph for you in real time, means that you can really go to town on kind of analysis. I would like you to try and hold the sensor next to your faces and then see what decibels is a whisper, a conversation between two people, a group talking, and a clap. Okay?
So clap in decibels is 86.3.
Yeah. For the whisper, we had 75.4.
Can somebody tell me, please, what kind of decibel level we get for a whisper?
75.4.
Brilliant, thank you. So we have about 75 dBA, okay, decibels. Okay, next one, we got a conversation between two people.
About 92 decibels.
92 decibels, dBA, okay. And we have now a group of people talking.
We got 110.
Thank you very much. Straight away, they can start to attach numbers to noises that they're making. So they can have a whisper, they can have a shout, they can have a clap, and they can then associate what those sounds do as to what their decibels are. It's almost like sometimes you're trying to dampen down their enthusiasm a little bit because they go mad for it, because they enjoy it so much. But that's what, as science teachers, we love. We love getting students engaged in their science, understanding the science, wanting to learn more, investigating. There we go. All right. And then...
These Year 9s are going to investigate the motion of a trolley rolling down a sloping ramp.
And I can work out how fast it's going at different points. Now, this is where the technology comes into it. Okay? Now, I'm going to have to do this experiment time and time again because I want to know, after it's travelled 20 centimetres, what its speed is, after it's travelled 40, 60, 80, 100. So how am I going to do that?
Take photos, and the time distance between them is... I don't know.
Good idea. That's a really good idea. I could take photographs, OK? Yes. What about you? What do you think? Come
on. Well, would you put laser beams on the track, and then as it breaks the laser beam, see when, and then when it breaks the other one, see when that happens, and then get...
That's a clever idea. And in fact, it's very close to what we're going to do. Well done, Daniel. OK. So let me show you what we're going to use. These things are called light gates. What they have inside here is a small little light sensor on that side, and this one gives out light. Now, when we connect this to the computer, as the truck falls down the ramp, it will cut the beam of light, pretty much like Daniel was saying, okay? And then, when it's gone past again, it will then detect the light. If we tell the computer how long that piece of card is, it will automatically work out for us how fast the vehicle's going, okay? So what you're going to do is, once you've set your ramp up, you're going to choose at what distances you're going to measure the speed, and then you let go, and the card has to cut the light beam without hitting it, okay? That will be for 20. Then you'll do the same thing, making sure I drop it from the same point again, but this time I'm going to hold the light gate at 40. All right, guys, off you go. They've already bounced it. This is the first time they've used the light gates, and setting them up takes a little bit of time. Using it with quite a large piece of equipment, I mean, you're talking about a lot of skills here. You're talking about coordination, you're talking about management, you're talking about group skills. All these things have got to come all at the same time in order for this practical to work. And I think, you know, they did really, really well, and they were able to actually work as a group, assign roles to certain people. You do this, but you do that bit. And they did that really well. And using the equipment for the first time, within 15, 20 minutes, once they knew what they were doing, that's it. And that's the beauty of the youth today. They can do that. They're so ready just to pick up and adopt new technologies. They don't have a problem with that.
So that's 20, that's 60, that's 1 metre.
It's not a difficult concept. What it is, though, it's a chance to actually collect data and interpret data and actually get reproducible results of which they can be critical about in real time.
Right at the top for 20 centimetres, you just have 1.172 metres per second as an average speed. Right, and at 80 centimetres, we have 1.861. So we must deduce that it will accelerate.
And how would they have done this without the light gates?
You'd have to do it by eye and use stopwatches, things like that, so it'd be a lot harder. Where's our line graph?
Third one.
Yeah. Line,
We need
next,
Or maybe a scatter.
series in...
Very good, I like it. That's a nice graph. Yeah, the fact that they could do it so easily, so quickly, and get results, and with one short lesson get a nice graph and able to come up with a prediction.
So you could say that there'd be a good correlation.
There's a good correlation between the two, yeah. And it's that skill that is very difficult to teach, and it's very difficult to get that idea across, and that's the hard to teach part of the topic.
This morning we're going to have a look at changing another variable in rate of reaction experiment.
Chris Mason is Head of Science at Salandine Nook High School in Huddersfield.
Now already you should be starting to think about what effect...
He's working with his Year 11s to investigate rates of reaction.
Can anybody predict what we think might happen if we vary the temperature of the sodium thiosulfate? Gina?
If it's warmer, then the reaction will happen quicker.
OK, if it's warmer, the reaction will happen quicker. That's good. Can anybody give a reason why they think that might happen? Stephen?
The particles will have more energy, so they'll collide and have more effective collisions, which means that they'll react.
Yeah. So they'll react quicker. So the key word that we were using there was effective collisions.
The practical session involves investigating the reaction between sodium thiosulfate and hydrochloric acid, which will be part of their coursework.
49.
Here, the students carry out this reaction at different temperatures, measuring the differing times the reaction takes to complete.
1 minute 40.
The reaction is complete when the black cross on the paper is obscured by the cloudy precipitate. Once they've got a set of results for reaction time against temperature, they move to the computer room.
What I'd like you to do is exactly what it says on the board. Use the smart book, and there's a link to the smart book there, C6. It does work to help you interpret your data. And then, key point here, remember that in your coursework, you will need to fully explain why the rate of reaction changes. And on page 39 in your notebook, I've actually put the mark scheme from the exam board, which shows you how far you need to go to get the full marks.